Hello, everybody. Here's some examples of how to set up and use the buoyancy force in like a real question. So what we do is say, let's come up with some examples. Say I have a person, all right? Here's a person. And a person, as we've discussed, say a person has a mass of 60 kilograms, their density is around, so that's the density of our object. A person is our object. They're submerged in the fluid of air. So first of all, this is what I mean by orientation. We're orienting ourselves with what the question is. So a person submerged in air. There is always a thin layer of air beneath your feet, unless you're wearing suction cups, which seals it. Air comes in. Air is little molecules. They come in everywhere. So you're going to have pressure forces pushing up, pressure forces pushing down, but ultimately there's a buoyancy force acting on the person. The density of the object, the person, is 1,000, but the density of the fluid, air, of course, is 1.225. So please differentiate between the object density and the fluid density. Remember, buoyancy depends on the fluid density because the buoyancy force is what the fluid is doing to an object. So the buoyancy force is caused by the fluid pushing up because it's squeezing from all sides due to the pressure. More pressure on bottom than on top, so you get an upward force always of this value depending on the volume of the person. So when we're drawing our force diagram, by the way, I say force diagram because in a force diagram, what are you drawing? You're drawing forces. Force diagram, step one, draw force diagram, uh, draw all forces. Some of you might have heard this referred to as a free body diagram. I don't really understand that term. I don't get it. To me, it doesn't make any sense because this is not free. It's under forces. So let's draw those forces. Let's say what it is. Don't give it a different name. Let's say what it is. So I hope that makes sense. We're drawing a force diagram, so we're drawing all the forces. Don't draw the net force. Don't predict the answer. All right. Don't predict the answer. Don't draw F net. What you're going to do is just draw all the forces. You're going to label a positive or negative direction, right? And then two, you're going to do F net equals MA. F net, this is so important, guys. F net comes from the diagram. You're not drawing FNet in the diagram, but you're solving for FNet from the diagram. There's two differences. So don't draw FNet first, assuming what it is. Let it come from the diagram. Big deal here. Once we get used to this 1-2 step, it's easy, logical progression. The forces we know. This force depends on volume and points up. Gravity points down, depends on mass. Boom. Mass of the object. So here's what we're going to do. Let's go to the next slide. There it is. Boom. So I have my person, Ready? It's my person. There's two forces. mg pointing down, fb pointing up. I'm going to declare up to be positive, but I don't know whether it's positive or I don't know, sorry, which one, where it's going to move. I'm just going to say up is positive just for fun. But that's a choice. I could make down positive, but I'm going to choose up. Great. So I've drawn my forces. This is my step one. Done. That was easy. FB is up, therefore is positive. MG is down, therefore is negative. Only because I've chosen my positive direction. Two, I write F net equals MA, and I plug in F net from the diagram. So what is F net? It's going to be FB minus MG. I don't know which one's bigger, and that equals MA. Don't assume the result. Don't do five steps at once. Just do this and then now I'm going to plug in some numbers. So the mass of the person was 60 kilograms. So that gives me mg. So mg equals 60 times 9.8, which is 588 newtons down, right? Down as negative. So I'm not going to write negative. I'm going to write the word down, right? So I'm going to plug 588 in here. What is the buoyancy force, though? The buoyancy force is the density of the fluid times volume times g. The density of the fluid is air. Careful to not mix up density of person with density of fluid times the volume of the person. But what's the volume of the person? Well, the density of my person was 1,000. The mass of my person is 60. So therefore, the volume is going to be what? Uh, Density is mass over volume. So volume is mass over density, which is going to be 60 over 1,000, which is 0.06 cubic meters. Now, you might remember that for water, 60 kilograms is 60 liters. Great shortcut. But we need cubic meters for the equation. So be sure that your volume is in cubic meters. So we have 0.06 cubic meters for the volume of the person. That's an M. Times G 9.8 equals, let's multiply that all together, 0.06 times 1.225 times 9.8 gives me 0.72 newtons. Up. I'm going to plug that in here. So let's take a moment, make sure that makes sense. That's up, that's down. And what we're going to do is redraw our diagram now a little bit more clearly. FB up, MG down. Really, if I'm drawing this as a true vector diagram, what I would do is actually erase this arrow and draw it enormously tiny because this is 0.72 newtons up and this is 588 newtons down. Which one wins? Clearly, the weight of the person is way more than the buoyancy force. Do you know we're feeling a buoyancy force right now? So buoyancy force is on any object in a fluid, even if it sinks, even if it has sunk or sinks. Even if it has sunk or it sinks, there is a buoyancy force on any object in a fluid because there's still pressure, right? There's still the air pressure, so there's going to be a buoyancy force, but it's so tiny that we don't notice it. So the net force is going to be 0.72 up minus 588 down equals negative, right? I can do that in my head. 587.28 newtons down. So if I stand on a scale, careful, yes, we referred to pressure forces as buoyancy as normal forces, but there's another normal force if I stand on the ground or stand on a scale. That's another normal force. That's the ground, not air pressure, separate normal force, right? And I'm standing here. The normal force, I have mg down, fb up, right? So I have Fn plus Fb equals mg, up equals down. I have equilibrium, or I have Fn canceling my net force down, right? So Fn is going to equal 587.28 newtons up, meaning you actually weigh a little less. This is called apparent weight. That your apparent weight is actually a little less because you are, so mg, your apparent weight is mg minus fb. You appear to weigh a little less, meaning if you're on a scale, the buoyancy force is helping push you up. So the scale reads a little less. So this is going to be less than mg because of the buoyancy force, because of FB. So again, pause and revisit that. But either way, we've solved for the net force, and we can actually solve for our acceleration falling down if we want to by setting F net equal to MA. So I can set this equal to, let's do that actually next. So if I have, let's complete this. Oops. I have F net equal to MA. I had FB minus MG equal to MA. I had 0.72 minus 588 equal to mass, which is 60 kilograms times A. A is going to be my net force over my M, which is negative 587.28 over 60, which is basically going to be 9.8. But 587.28 divided by 60 kilograms gives me 9.788 meters per second per second. So because of the buoyancy force, if I were to fall through the air, I'm actually falling a little bit slower than G because of the upward buoyancy force. Isn't that amazing? We don't always talk about this. This is like, again, just like we don't talk about all the pressure we're feeling right now. We don't really realize that air is actually causing us to want to go up, but we ignore it. But 0.72 newtons, that's not nothing. I think that's interesting, right? I think that's kind of cool. Anyway, ends up being like half of a pound. So half of a pound difference, I think. No, sorry, less than half of a pound. This is like a sixth of a pound. I think it's like a sixth of a pound or something like that. We could do the conversion pretty easily, but I forget it in my head right now. About a sixth of a pound less. But you fall a little bit less because a little bit more slowly because the air is actually pushing you up. I think that's fascinating. Anyway, that's how you set it up. That's how you do all those questions. Cool. Let's do another one. Two. Let's have two objects of the same volume, but different masses. So we'll say V1, V2, M1, M2. Let's say I have M1 is 2 kilograms and M2 is 0.2 kilograms. Quickly, I can solve for this. Density 1 is 2 kilograms per liter. which is 2,000 kilograms per cubic meter, not relevant. Density 2 is going to be 0.2 kilograms per liter, which is 200 kilograms per cubic meter. Not relevant, but I'm solving for it. I mean, it's relevant, but it's not, we don't need it for the equations, but I'm solving for it. These are the object densities. And let's say that they're submerged in water. So my fluid density is 1,000. Be careful. Fluid density is different from the object density, right? And we need to be able to look at those numbers and know what they mean. So take a moment. That's how dense that is. That's how dense that is. That's how dense our water is, submerged in water. Right? We got water going on. And I drop them. What is the acceleration of each? And which has more buoyancy force? Great. Let's do it. So we'll start with the first one. Volume is 1 liter. I'm actually going to do them side by side. This would be cool. I'm going to get rid of the density of the object because that's not important because I already know my mass and volume. Remember, volume gives me FB, mass gives me mg. Volume gives me FB, mass gives me mg. That's the conceptual, so much so the conceptual most important thing is that this and this are what matter, right? Mass gives you mg, volume gives you buoyancy for both of these. Please know that concept. Big, big deal. Key concept, right? Volume gives you buoyancy, mass gives you gravity. Volume gives you buoyancy, mass gives you gravity. So I'm going to start here. Which has more FB? They're the same because same volume. Done. The buoyancy force for both is going to be density of the fluid times volume times G, which is going to be 1,000. Careful, that is the density of the fluid, right? Times 1 times G. What did I do wrong? No. No. It's going to be 1,000. I need, let's do a different color for this one. Need cubic meters. So instantly I want to convert volume to 0.001 cubic meters by dividing by 1,000 to go from liters. There are 1,000 liters in a cubic meter, so I need to divide by 1,000, and I have 0.001 times 9.8. And look at that, 1,000 times 1,000th gives me 1 times 9.8 gives me 9.8 newtons up for both. Great. Pause it if you need. I'm going to keep moving on, but that's important. All of that was important detail, right? So I have, again, for number 1 versus number 2, I draw my force diagram, FB up, mg down. Right now, I don't know which one is bigger, but I'm going to figure it out. For both of them, it's 9.8 newtons up, just because of their volume. So we're in water. Orient ourselves. What are we doing? We're in water. The pressure forces of the water are creating a force upward on both that is the same because they have the same volume. Now for this one, mg will equal 2 kilograms. Remember, m here is 2. M here is 0.2. Times 9.8 is going to give me 19.6 newtons down. So this is 19.6 newtons, which, I don't know. Maybe I'll choose positive to be down for this one. So if positive is down, Then I have F net equals MA. So I have MG minus FB equals MA. So my math goes over here. I have 19.6 minus 9.8 equals 2 times A. So I have 9.8 equals 2A. So I have A equals 4.9 meters per second per second. Sorry, that squeezed in there a little bit. Let me do that a little better there. 9.8 equals 2A. So I have A equals 4.9 meters per second per second. And since it's positive, it's down, right? So since this wins, I know my acceleration is down, which means it sinks. Obviously, to sink means FG is bigger. If I'm on a float, FB is bigger, and this is going to rise. And I know it's going to rise because I know the answer, but let's prove it, right? Let's assume we don't know the answer. I wonder if I could squeeze it in here. So I'm going to write this a little smaller. Right here, I'm going to say positive is up because mg is going to be 0.2 times 9.8, which is 1.96 newtons. So which wins? This wins. So it rises, right? This wins. So it sinks, right? So if I let it go, I don't give it any velocity. Even if I did give it a velocity, it would just pop back up. If I gave this one a velocity up, it would go back down because the net force is down. Here, the net force is up, so I know the acceleration is up, right? Because this one wins. Because up is bigger than down. So now I can solve for it, the actual acceleration, pretty easily. See if I can do this really neatly. F net equals MA. F net is 9.8 minus 1.96 equals 0.2 times A. I will skip that, but do it. 9.8 minus 1.96 is 7.84 divided by 0.2 gives me an acceleration of positive 39.2, which of course means up. I chose my positive to be up. And sorry, that's meters per second per second. Boom. So notice how this one's going down at half of gravity because buoyancy force is helping it. But this one's gravity is so low and the buoyancy is so high that this one is just flying up. This one is such a high speed. This one's what? What's 39.2 divided by 9.8? Is that 4? Yeah, that's 4 Gs. 4G up. Oh my goodness. That's just flying out of the water. So cool. We got it. Just review those. That's how we do this analysis, looking how each variable affects each force. That's the most important thing. Mass affects gravity down, volume affects buoyancy up. And so looking at those two individually affect the net force. Which wins? That's the question. I hope that made sense. If you're precise, take your time, be precise about what each variable is doing, and don't move on until you're 100% certain of visually what's happening. Never assume the answer. Always let the diagram and the numbers take you there, unless you do have an intuition, but please prove it. And if you see it, great. That's like the moment of realization where it starts to click. But right now we're following the procedure and setting it up so we know the physics takes us there. Hope that made sense. See you guys later.